Hello friends. This video is brought to you by mywayteaching.com.
Before extending remainder theorem to the polynomials, let us revise the remainder theorem for our real numbers. Say we have to divide 11 by 2. Then we know that 11 is called the dividend and 2 is called the divisor, and after division we get a remainder and quotient. We have also learned in our previous classes that dividend is equal to divisor into quotient plus remainder. Let us extend this study to polynomials. Consider two polynomials px and gx, and let us now learn to divide one polynomial by another. So, say we have to divide px by gx. We write the dividend and the divisor in the standard form as for the real numbers. So we have 3x square plus x minus 1 divided by x plus 1. Our next step would be to divide the first term of the dividend by the first term of the divisor. So that means we have to divide 3x square by x. This will give us 3x power 2 minus 1, which is equal to 3x. This gives us the first term of the quotient. That means in the quotient we have 3x. Our next step is to multiply this first term of the quotient with the divisor and write it under the dividend. So we have 3x into x is equal to 3x square. 3x into 1 will give 3x. Now we have to subtract, so we change the signs and our first term gets cancelled. We are left with minus 2x, and let us carry this down. We get minus 2x minus 1. From the third step, we can clearly understand why we had done the division. Because when we multiply the first term of the quotient with the divisor, we get such a term so that the first term gets cancelled when we subtract. Now in the next step, we will treat minus 2x minus 1 as the dividend and x plus 1 as the divisor. So let us divide minus 2x by x. We are repeating step 2, considering this to be the dividend. We get minus 2. So minus 2 is the second term of our quotient. So now we will multiply minus 2 with x plus 1. It gives minus 2 into x will give minus 2x, and plus 1 into minus 2 will give us minus 2. Now we have to subtract, so the signs will change. First term will get cancelled and we are left with plus 1 as the remainder. Now, since 1 is a constant polynomial, its degree is 0 and x plus 1 is a linear polynomial, its degree is 1. So, we can stop our process here, as the sixth step says that the process continues till the remainder is 0 or the degree of the remainder is less than degree of divisor. So we have seen that when we divide px by gx, we get quotient equal to 3x minus 2 and remainder as 1. Let us check the authenticity of this rule for the polynomials. So let us substitute the values of divisor, quotient and remainder in the right hand side and solve to check whether it gives us the dividend. On substitution of the value, we get the following expression. Now let us solve it further. We get x into 3x as 3x square, minus 2 into x gives us minus 2x, plus 1 into 3x is 3x, 1 into minus 2 will give us minus 2 and plus 1. Let us solve this further. We have 3x square plus, on solving this we get x, minus 2 plus 1 will give us minus 1, which is same as px, that is our dividend. Hence, this rule applies to polynomials also. So we can say that in general, if px and gx are two polynomials such that degree of px is greater than or equal to the degree of gx, then we can find qx and rx such that px is equal to gx into qx plus rx. And here rx will be either equal to 0 or degree of rx will be less than degree of gx. We just now discussed that for polynomials, dividend is equal to divisor into quotient plus remainder holds, and remainder can take value either 0 or any polynomial whose degree is less than the degree of divisor. Let us discuss the way of finding remainder without actually dividing the two polynomials. Suppose we have to divide px by gx. Then to find rx without actually dividing px by gx, we equate x plus 1 equal to 0 and get x equal to minus 1. Now let us find the value of px at x equal to minus 1. We get p of minus 1 equal to 3 into minus 1 whole square plus of minus 1 minus 1, which is equal to 1, which is same as the value obtained of the remainder after actual division. So we can say remainder obtained on dividing px by gx is same as the value of px at the 0 of the polynomial gx. We are saying so because in our first step, while equating gx equal to 0, we are actually finding the 0 of the polynomial gx and then substituting that value in px. Now we are in a position to state the remainder theorem. Let px be a polynomial of degree greater than or equal to 1. Then if px is divided by x minus a, remainder is value of px at x equal to a.